Okay, very good. So today, guys, we're going to talk, we're just going to start with an 8.3 here, talking about relative rates of growth. We're actually going to use some of the things we've been talking about, especially the last section, the Hopkins rule. We're going to use that quite a bit in here, to help us figure out if we have two different functions, which one grows more quickly than the other. Now, there are some, if we compare them side by side and look at the graphs, that sort of thing, it's pretty obvious which one is going to grow more quickly. But we have kind of a method where we can do this for any function that we want. So you can probably guess the correct answer here. But, show you how to verify this too. Alright, so let's say we get these two functions, f of x equals x, and f of x equals x squared. So based on what you know about those two functions, which of those two do you suppose is going to grow more quickly? G of x, right, x squared, okay? And why do you say g of x? Well, it's not technically exponential, but what about for exponential will be something to the x, right? So, but you got the right idea, though. What's the difference? Yeah, one's got an exponent, one's squared, okay? And when you square something, as opposed to just leaving the number alone, it makes it bigger, right? So as x increases, the result of squaring it is going to make bigger and bigger and bigger and bigger numbers, and so it's going to grow more quickly. And if you look at the graphs of these two things, too, you can kind of see that as well. So f of x would look like that. G of x something like this. So g of x, as you go out, has a steeper slope, right? So that's really kind of what we're looking at here. So as we increase x, which one is sloping up more than the other one? That sort of thing, okay? We can thing kind of like when we were looking at finding horizontal asymptotes, when we were doing L'Hopital's rule, making a function out of these two. So we're really concerned with the limit as x goes to infinity of one function divided by the other. Okay, so if this limit equals infinity, that means whatever was on the top is growing more quickly. Okay, does that make sense? That if the top of the fraction is growing more quickly than the bottom of the fraction, then the entire thing goes to infinity. Does that make logical sense to you? Okay, so, all right, so if it equals infinity, f of x grows quicker. Likewise, if it equals 0, that means whatever's in the bottom here is growing more quickly then. Okay, so g of x is growing more quickly. All right, and if it equals a constant, they grow at the same rate. And if the limit ends up being something for some reason, then we just can't determine which one's going to be more quick. Okay, so but this is kind of the big kit and caboodle here. We're going to take this idea, we're going to compare some functions, we're going to try and set up fractions, and if we need to, do a little L'Hopital's rule on it to get us through it. So let's take a look at this one. We said g of x was the one we expected to win, right? So let's see if that works with using this little process here then. So we're doing the limit as x goes to infinity, f of x over g of x over x squared. Okay, now a couple different ways you could look at this then. Number one, if you wanted to figure out what form we have to start with here, this is an infinity over infinity form, right? You do L'Hopital's rule to the derivative of the top, derivative of the bottom. Or you could look at this as a rational expression that can be simplified. X over x squared, what can I do to that? You can cancel an x, okay? So I'm just going to do that, because that's easier. All right, so what is the limit as x goes to infinity of 1 over x? 0. Remember we talked about that the other day? Okay, in the limit world, if you have 1 over infinity, it's technically 0, right? So this works out to 0. So, therefore, g of x equals x squared grows more quickly. You ever seen this little symbol before with the 3 little dots? Some of us. Yeah, it means therefore. So therefore g of x equals x squared is, the quicker one. Okay. So let's try. The square and g of x was natural log of x. So here, before we do that, let's draw sketches of these two graphs real quick. So I think this is one, remember the first one that we did, it was obvious just by looking at what we had, which one was going to grow more quickly. This one I think is an interesting one because they look very similar. Like a square root function looks something kind of like that. Think about what the graph of a natural log looks like. It's almost identical. It doesn't come off the origin. It's off just a little bit. It comes up kind of right here and heads over. So by inspection, this one's not a real easy one to make a call on, right? Square root, natural log, don't really know. So a limit's going to help us on this one to know for sure which one is growing more quickly as you go out. So if we do that, limit as x goes to infinity. And it doesn't matter which way you make your fraction, right? Because depending on the outcome of it, you should be able to pinpoint which one wins. But because we did this as f of x and this is g of x, we'll go ahead and do it that way. So put the square root on the top. It is important to note, though, because sometimes, like you might run into a situation where if you set up the fraction one way, you can't really simplify it or do anything to it or work with it, and you kind of get stuck. But if you were to just simply flip that fraction around and make the f of x the g of x and vice versa, then it's something you can actually do. So if you run into a roadblock where you get stuck, you can do that. You can go back and just switch it around and try it the other way. But let's see if we can get through it this way, though. So right now, can I evaluate this thing? Or is it one of those indeterminate forms again? What's the square root of infinity? Infinity, right? Look at the graph, right? Because this thing continues to increase, that's infinity. Same thing with the natural log, right? Natural log of infinity is infinity because it just keeps going up. So we have an infinity over infinity form. And unfortunately, unlike the last example we did, we can't just do a little cancellation, simplify it, that sort of thing. We have to actually do some L'Hopital stuff here to get this one done. So, limit as x goes to infinity. Derivative of the top, it's a square root. So what do we got? One negative 1/2. All right, and then natural log on the bottom there. So derivative of a natural log. 1 over x. Okay. All right, so we're going to want to clean this up just a little bit because we want to try and make this just one fraction again. So let's see what we got. At the top here, this would be 1 over 2 square root x divided by 1 over x. So we can do that. Take the reciprocal of that denominator and multiply it. So this becomes, let's see, so the x would go on top. So we got x over 2 square root x. All right, so can we evaluate that? Or do we need to go again? Got to go again. Still have infinity over infinity. Okay? So, yeah. So derivative of the so where does that put us? Derivative of x. Derivative of 2 square root of x. Well, it's going to be the same thing as what we got when we did the derivative of the square root, except the 1/2 is going to cancel with the 2. To the negative 1/2 should be then. Okay, but since we got an x to the negative 1/2, and it's in a denominator, we can bring that up on the top. So this is actually just square root of x at the end of it here. So, can I evaluate that? Sure. What's the answer? Infinity. So what conclusion can I make? It does. Yep, the square root of x actually grows more quickly than the natural log does. So, therefore, f of x equals the square root of x grows quicker. Okay? Seems like kind of a simple thing, and maybe kind of a duh issue, but it does happen. So with these, when you're working on your homework with this stuff, remember, unlike the last section, this is not your answer, right? The question was asking which function grows more quickly, so don't forget to actually make that statement somewhere in the problem that, oh yeah, it's this one that wins or whatever. Okay, this one grows more quickly. Statement needs to be there. So, all right. Let's try another one here. I think we got probably time for just one more, and then we got to call it. So, let's compare squared, and we'll kind of expand out a little bit here away from your basic functions. And how about this? How about x squared and then x squared plus sine x? So one where you're pretty familiar with what the graph looks like, not so much. X squared plus sine x, I don't know. So think? I mean, just by looking at the equations, which one do you think is going to grow more quickly? Or are they going to be the same? Any ideas? Heading into this one?
Be the same.
Think the same? Yeah. Okay, what makes you say that?
Because they both kind of grow the same, but
Mm-hmm.
plus sin x would kind of just wait a little bit. The sin x goes up.
Yeah, sin x doesn't really go anywhere, right? It's just back and forth, up and down, up and down, up and down. And they both have then the x squared component to them. So it seems reasonable that they should just grow at the same rate then. Because adding a sin x to it isn't going to change anything as far as how quickly it's growing. So, yes. Squared. Which, if you remember your rules of limits, then make this to infinity of 1 plus x goes to infinity sin x over x squared. And the answer to this, what's the limit as x goes to infinity of 1? Just 1, right? So plus limit. Okay. So then the question becomes, is that a L'Hopital rule friendly little fraction there or not? Or is there something else that I might need to do the limit? So take a look at it. Is it in indeterminate form? Is it infinity over infinity or 0 over 0?
Just a constant over infinity.
Yeah. So it's, well, you know what? It's not even a constant, though. That's the problem with sine is sine doesn't have a discernible place it's going to be when you're at infinity, right? Because it just keeps fluctuating between -1 and 1. So you really don't have anything that you can say. Like the limit as x goes to infinity of sine x doesn't have an answer. I don't know, because it just keeps going back and forth. If it continued to go up, like if it fluctuated, then it's going to infinity, or maybe it's leveling off as it fluctuates. But it's not doing any of those things. It's just continually between -1 and 1, -1 and 1. I got nothing I can do with that. So I can't even begin to do a L'Hopital's rule here because I got nothing to say about this top part here. So we need to come up with a different way to try and evaluate that limit right there. So it has a certain here that we've done in the past. Anybody recognize it? What we might have to use to evaluate that limit instead then? Has a sign in it. It's in a fraction. No? They're tasty to eat. The sandwich theorem. Yeah. You know, then here. It's definitely smaller than sine x over x squared. Okay, the way we between -1 and 1. So right? Keep the x squared on all of them, because that's going to be the same. So we know he's definitely caught between -1 and 1, so we can sandwich it that way. Okay? So is what? 0. On here. What's that limit? 0. Essentially, right? So what's our conclusion then? They grow at the same rate, just like we thought it was going to be. Yep. And there's going to be some more of these that get kind of tricky, and that's what we're going to focus on Monday. So, yeah, if you guys could come back Monday, we'll take care of that together, and then you'll have some time to work on homework. Okay, I think we're good. Yep. All right, so what we're going to look at today, guys, like I said, are two things. Number one, using graphing to determine relative rates of growth, and then number two, using this transitivity of growth to help us. So let's start with graphing. So if we want to look at a graph, what we're actually going to graph when we do it this way is we're going to graph not the two functions individually that we're comparing, but the two functions divided by each other, because that's really how we set up those limits before. Was you do the limit as x goes to infinity of f of x over g of x, and then the result of that could be one of three things, and based on those three results, each one gives you a different conclusion to reach. So if it went to infinity, then the f of x, whatever was on the top, was growing more quickly. If it went to 0, g of x, whatever was on the bottom, was growing more quickly. And if it came out to a constant, they graphed it, or they were growing at the same rate. Okay? So if you graph f over g, basically you're looking for the same three results, just in graph form. Okay? So if you see the limit on the graph, then you know. So if I see something that's doing something like this, when I graph f over g, what can I conclude? What is the limit as x goes to infinity of that graph? Yeah, right? So what can I ultimately conclude then from that graph? Which one grows more quickly, f or g? F, right? Okay, what if I had a graph that looked like this? Where the limit as x goes to infinity of f over g equals 0. So which one's growing more quickly then? G, right? Said it's doing the same thing.
seeing it in a graph. So if you're allowed to use a calculator, this process is actually pretty easy. You don't have to worry about manipulating the limit and all that kind of business. Just draw a graph or sketch a graph or do it on your calculator, take a look, and see what's happening. And then obviously there's still that third option. So if it ended up doing something like this, okay, approaching some kind of horizontal, pretend like that's straight. Let me change it up here real quick. So if we had something like this. Okay, so it's approaching some sort of horizontal asymptote. Okay, so we're approaching some sort of constant there. Then we know that f and g grow at the same rate. Sometimes where you're looking at functions where you're probably not going to be able to do much with it algebraically. Like trying to manipulate it is going to be very difficult, possible at all. So that's where this process comes into play. We want to go into this. So let's try that once. I'll give you a couple here to take a look at. Let's do 3 of x is x squared. G of x a square root of x to the 4th plus x. And h of x equals square root of x to the 4th minus x to the 3rd. Okay, now this one we can make a decent guess, I think, maybe just by inspection. So, what do you think is going to be true about how these three all compare? If you had to make a guess. We got x squared, square root of x to the 4th plus x, square root of x to the 4th minus x to the 3rd. G is the fastest, then F, then H. Okay, what makes you say that? Mm-hmm. 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 Okay, so if you consider just the first part of each one of those square roots, it's pretty much the same, but then because this has something a little bit added to it, you think that would go a little faster, and this one's getting something subtracted from it, so that maybe would go a little slower. Okay, anybody else? Strong opinions, one way or the other? All right, well, let's take a look. Let's see if rate. All right, so we have to do a little bit of graphing here. Like we have to do a couple different graphs because we have three that we're trying to compare. Okay, so let's compare just f and g for right now. Okay, so all right, so on your calculator, go ahead and graph f of x divided by g of x. Take a look and see what. So, what conclusion do you think we should make about the relative rates of growth of F and G based on what you're seeing? They grow at the same rate. Yep. Sorry, Rachel. It looks like this, at least this is what I had on the window I used. It looks like it's leveling off to a constant on that one. So yeah, these are going to grow at the same rate. Oops. Because our graph did something kind of like that. Okay, so whoops. All right, so F and G grow at the same rate. All right, well so let's compare G and H once I fix this. How the heck did that happen? Okay. Anyway, all right, so I'm going to graph the G function divided by the H function. See how those two compare. Bless you. All right, so again, based on what you're seeing, growth of G and H. Say that a lot louder. They're the same too. Yeah. Graph that looks something kind of like that. Okay, it's decreasing, but it's still leveling off, right? It's still approaching a constant. It looks something kind of like that. So for that one, we can conclude the same thing. G and H. So this actually kind of leads us into what we're going to talk about next. But what can you conclude about the relative rates of growth between F and H then? What should it be? Same, right? If F and G are the same, G and H are the same, F and H should be the same too. Look at the graph if you'd like to verify it. However, we know that those have to be the same too. All right, so that means that all three of these, F, G, and H, all grow at the same rate. Well, let's go back to the first three that we're looking at, and like I said, trying to kind of make a guess. Does that make sense that they're the same? Or are we still kind of confused? Rachel doesn't like it because she's the one that put her neck out there. It's different. Well, the only reason that they're the same is we've talked about with end behavior in the past is if you have multiple terms, whether they're under a square root symbol or not, whatever has the highest power really dominates, and the rest of it is pretty negligible as we approach infinity. So this plus x, this minus x to the third, they don't really do much because you're raising this part to the fourth power, and as you get really, really large numbers, this makes so much more of an impact than this, and this makes so much more of an impact than that, that they might as well not even be there. Okay? So if we were these three, x squared, square root of x to the fourth, square root of x to the fourth, it's all pretty much x squared, right? So it's all growing the same as what x squared would when you get to really big numbers, okay? So we would expect those then to all grow at the same rate. So, and they do. They do. So, all right. So this whole transitivity thing, okay, we did it right here, okay? We found there was one function in the middle, this g function, that when we related it to f and when we related it to h, we got the same conclusion. So we're able to use the transitive property. If a equals b and b equals c, a equals c, that's the transitive property of equality, right? Well, there's a transitive property of this stuff too, okay? If f and g grow at the same rate and g and h grow at the same rate, f and h grow at the same rate. We just did that right there using that same kind of idea, okay? You guys naturally were able to apply that. Now, it works if things grow faster too. If f grows faster than g and g grows faster than h, what could I conclude? Right. F is faster than g, g is faster than h. Well, f certainly should be faster than h then, right? Or what if f grows more slowly than g and g grows more slowly than h? Same kind of thing. F should grow more slowly than h. So you can use that transitive type idea with more than two, okay? You just got to compare, you got to use one, the second one and two second comparisons, and then you can use whatever the results are to kind of line them up from least to greatest, okay? Or if they're all the same, like this one, you can just say they're all the same. We're going to try this idea. We're not going to use the graphs anymore. We're going to go back to doing it by hand because I'm going to give you a few here that you can do by hand. But the trick is going to be with these, though. You're not going to have three. You're going to have two that you're trying to compare that you might not necessarily be able to compare directly, but you have to come up with a third function that could be that intermediate one that you can compare to both and try and use to show whatever it is you're trying to show. So we'll just jump right into this example then. So if we've got, what are the ones I wanted to do? X equals the square root plus 5 and g of x equals 2 square root x All right, we want to compare those two functions and see which one grows more quickly. Now, if you try to do a fraction with just these two by themselves and try to apply the L'Hopital's rule and all that, it gets kind of messy, and you're going to run into some roadblocks. With a pair to these two, that might help me out to see which one grows more quickly, or if they grow the same. Okay? So you have to have kind of a little bit of an intuitive guess as to what's going on before you can really make a good determination of what that other function should be. And you want to try and keep it something simple, too, so that it'll work. So these two, think about what we talked about before. If I've got terms added together, the ones with lower powers are pretty negligible as we get out pretty far, okay? So in this one, this little plus 5, doesn't really matter, right? This minus 1, even though it's all being squared, even though this is all under the square root, again, this minus 1 doesn't really matter, okay? So what do you think is going to be the case with these two? F beats G, G beats F, they're both the same. If you get rid of the 5 and the 1, what's going on then? It looks like they might be the same. Because what's the square root of x squared? x. 2 square root x squared before x, but it's still an x, right? The power is still just to the first power. So it seems reasonable that they would be the same. What's a nice, simple function that I could use that I know would end up being the same with these? X, exactly. Okay, so we're going to introduce h of x, which is just x. Okay, so then we're going to do some limits again. Okay, we're not, like I said, we're not doing the graph stuff this time. We're going to make some limits and do a little comparison here and see if we can prove that these all grow at the same rate. So if we take f of x with the h of x, then we've got the limit as x goes to, bless you, infinity, square root of x squared plus 5 over x. Alright, now I could jump into Allah Hopital's rule here and all that. Need it though. Because I can do a little bit of manipulation on this one and rewrite it. Okay, so I'll see the little trick I just did there. I can make that x in the denominator an x squared if I include it under the square root, because the square root of x squared is just x, right? So I just kind of did that backwards. That might seem a little weird that I made that more complicated by doing that. But if you look what's under the square root now, if there's anything that can cancel, now I'm allowed to do it because it's all under the square root as one big thing. So these x squareds right here, cancel those. I'm still going to divide by x squared as well. This becomes now a limit that I can actually calculate without having to do anything else to it. Okay. Remember what we talked about. In the limit world, anything divided by infinity equals what? 0. So what's the answer to this limit? 1. Right? Because that 5 over x squared is essentially 0. 1 plus 0 is 1, square root of 1. This is 1. So we've now verified that, yes, indeed, f and h grow at the same rate. So if we can show that g and h grow at the same rate, we've proved that f and g actually grow at the same rate. So let's do the same thing with g. Alright, so we got the limit. X approaches c. Of the g of x over the h of x. Now I'm going to do another little manipulation here that's pretty much the same kind of thing we did up there. And turn this into one big, just the numerator that's being squared. I change the denominator to make it all being squared at the same time, using the same kind of idea like I did last time. What would it need to be? Square root of x, right? Right? Because the square root of x squared is just x, so I could, pull that out like that. Now take a look. Kind of same type of thing as last time. I can cancel a little bit, right? Those square roots will cancel. So what's that limit equal to? Because this fraction here is essentially 0 again, right? 4. Now, the important thing is, again, I ended up with a constant, right? Both times. So I've proven that f and h grow at the same rate because I got a constant with my limit. And I've also proven that g and h grow at the same rate because I got a constant as the answer to my limit. So I can conclude from that f and g must also grow at the same rate. Okay? So here's how I'm going to write my conclusion then. So since the limit as x goes to infinity of f over h and the limit as x goes to infinity of g over h both constants, h grow at the same rate, and g and h grow at the same rate. So we can conclude f and g grow at the same rate. Done. All right, so when you're using this transitivity thing, you got to include some kind of a little explanation about how it is exactly that you used it, okay? So something like that would be perfect. Okay, so any questions about any of the stuff that we've talked about today before I set you loose? All right, well, I'll let you guys see everything that you need.